Hello friend, and welcome to Science for Sleep. Before we begin, here's something quietly surprising. When a candle burns, the solid wax is not what's on fire. The heat melts the wax, lifts it through the wick, and turns it into an invisible vapor. That vapor is what the flame consumes. What you're seeing is not solid wax burning, but wax that has changed form. This simple idea helps us understand what a candle truly is. A candle is not just an object with a flame on top. It is a small, carefully balanced system that manages heat and fuel in a slow, controlled way. Every part of a candle has a role, and each part responds gently to the others. At its most basic level, a candle is a self-feeding fuel system. The wax stores energy. The wick moves that energy. The flame releases it. Solid wax on its own does not burn. It is too stable. It must first be warmed. As the candle is lit, heat from the flame melts the wax near the wick, turning it from a solid into a liquid. This liquid wax then begins to move upward through the wick. The wick acts like a very small pathway, filled with tiny spaces that allow liquid wax to rise slowly. This movement is not forced. It happens naturally, guided by the structure of the wick itself. As the liquid wax reaches the top, the heat of the flame becomes strong enough to change it again. The liquid wax turns into a gas. This wax vapor is invisible, but it is the true fuel of the flame. The flame surrounds it, consumes it, and releases light and heat in the process. As long as this vapor continues to form, the flame continues to exist. At the same time, the flame provides the heat needed to keep the cycle going. It melts more wax. It creates more vapor. It sustains itself without rushing. If the balance shifts too far in either direction, the system corrects itself or stops. If there is too little heat, the wax does not melt fast enough, and the flame shrinks. If there is too much heat, the wax rises too quickly, and smoke or soot can appear. A well-made candle lives comfortably between these extremes. This is why a candle flame feels steady and calming to watch. It does not leap or roar. It adjusts slowly to small changes in air movement, wax level, or temperature. Even when it flickers, it does so gently, returning to balance again and again. Despite the many shapes and styles candles come in today, this process remains the same. A tall pillar candle, a small tea light, or a candle in a glass jar all rely on this quiet exchange between wax, wick, and flame. The materials may vary, but the behavior stays consistent. The light produced by a candle reflects this controlled process as well. Candlelight is soft and limited. It fades quickly as it moves away from the flame, creating a small pocket of illumination rather than flooding a room. This makes candlelight feel contained, almost personal, as though it belongs only to the immediate space around it. Long before electric lights, candles were used simply because they worked. Today, they remain because of how they behave. A candle does not compete with darkness. It shares space with it, shaping the environment gently rather than overpowering it. When a candle is lit, nothing dramatic happens. There is no sudden brightness, no loud sound, just a small flame settling into place, beginning its slow and steady work. Understanding a candle as a system, one that releases energy gradually through carefully timed changes, helps explain why it has remained part of human life for so long. Next, we'll begin by looking more closely at the wax itself and how this quiet material stores energy, waiting patiently to be released. Scent is one of the most noticeable qualities of a candle, yet it is also one of the most quietly managed. A candle does not release fragrance simply because it contains scented oil. The process depends on temperature, timing, and balance. Wax acts as a holder for fragrance oils. When fragrance is added to melted wax, the scent compounds become suspended throughout the material. As the wax cools and solidifies, these compounds remain locked in place. At room temperature, very little scent escapes. The wax holds its fragrance patiently, waiting for warmth. When the candle is lit, heat begins to change that stillness. As the wax near the flame melts, fragrance molecules gain energy. They move more freely within the liquid wax and begin to evaporate into the air. This evaporation is what allows scent to travel through a room. The process is gradual and controlled, guided by the temperature of the melt pool. The size and warmth of the melt pool play a central role. A shallow, evenly heated pool releases fragrance steadily. A pool that is too cool may release very little scent. A pool that becomes too hot may release scent too quickly, causing the fragrance to feel strong at first and fade sooner over time. This is why scent strength is not simply a matter of adding more fragrance oil. Fragrance performance depends on how evenly and consistently the wax warms. Different waxes interact with fragrance in different ways. Some waxes absorb fragrance oils easily, holding them evenly throughout the candle. Others have limits to how much oil they can retain while still burning cleanly. When these limits are exceeded, fragrance can separate from the wax or interfere with combustion. To manage this, candle makers often adjust wax blends or use additives that improve fragrance retention. These materials help bind fragrance oils within the wax, allowing them to remain stable as the candle warms and cools. The chemistry of the fragrance itself also matters. Fragrance oils are made up of many different compounds, each with its own evaporation point. Some notes evaporate quickly and are noticed early. Others evaporate more slowly and appear later. This layering contributes to how a candle's scent develops over time. As a candle burns, the fragrance does not emerge all at once. Instead, it unfolds gradually, shaped by the changing temperature of the wax. The first lighting may produce a lighter scent, while later burns allow deeper notes to become noticeable as the candle reaches a more stable melt pool. Container candles are often designed with fragrance release in mind. The vessel holds heat around the wax, helping maintain a consistent temperature. This supports steady evaporation and allows scent to disperse evenly, rather than in brief bursts. Air movement also influences how fragrance travels. In still air, scent lingers and spreads slowly. In moving air, fragrance disperses more quickly and may feel lighter. The candle itself does not control this. It releases scent at the pace set by heat. The environment carries it the rest of the way. Softer wax blends are often chosen for scented candles because they respond gently to heat. They form melt pools without excessive temperature spikes, allowing fragrance to evaporate at a controlled rate. Firmer waxes may release scent more slowly, depending on how they melt. When a candle is extinguished, fragrance release stops almost immediately. As the wax cools, evaporation slows and then halts. The remaining fragrance remains locked in the solid wax, unchanged. This pause allows the candle to be used again later without losing its stored scent. Over repeated uses, fragrance gradually decreases as molecules are released into the air. This process is slow and predictable when the candle is well designed. The scent does not vanish suddenly. It fades gently over many hours of burn time. A well-scented candle does not overwhelm the senses. It fills the space quietly, staying close to the flame and spreading outward without force. The goal is balance, not intensity. Strong fragrance does not come from excess. It comes from control. The wax, the fragrance, and the heat must work together. When they do, scent becomes part of the candle's rhythm. It rises as the wax warms, rests when the flame is gone, and returns when heat invites it again. In this way, fragrance behaves much like the flame itself. It appears only under the right conditions. It spreads gently, and when those conditions fade, it withdraws, leaving the candle ready to begin again. Wax is the quiet heart of a candle. It sits still, holds its shape, and appears inactive, yet it exists for one purpose: to store energy until heat invites it to change. At room temperature, candle wax remains solid. This solidity is important. A candle must be firm enough to stand, to support the wick, and to remain stable over long periods of time. If wax were liquid at normal temperatures, a candle would lose its form. If it were too hard, it would resist melting and fail to feed the flame. Candle wax is chosen because it rests comfortably between these extremes. Most candle waxes are made of long chains of carbon and hydrogen atoms. These chains are packed together tightly when the wax is cool, giving it structure. In this state, the wax does not evaporate, does not release energy, and does not interact much with the surrounding air. It simply waits. When heat is applied, that stillness begins to loosen. As the flame warms the wax near the wick, the long molecular chains start to move more freely. The solid wax softens, then melts, becoming a liquid. This change does not release energy yet. It only prepares the wax for its next role. In liquid form, wax can travel. The melted wax collects around the base of the wick, forming a small pool. From there, it begins its slow journey upward. The wick draws the liquid wax along its fibers, lifting it gently against gravity. This movement is steady and measured, governed by the thickness of the wick and the properties of the wax itself. Different waxes melt at different temperatures. Some soften easily with gentle warmth. Others require more heat before they begin to flow. This melting point affects how quickly fuel becomes available to the flame and how wide the melted pool becomes over time. A wax with a lower melting point may form a broad, shallow pool. A wax with a higher melting point may hold its shape longer, feeding the flame more slowly. Neither approach is better. Each creates a different rhythm. Once the liquid wax reaches the upper portion of the wick, the temperature increases again. Here, the wax undergoes another change. The heat is now strong enough to break the wax into vapor. This vapor is invisible, but it carries the stored energy that has been locked inside the wax since it was formed. Only at this stage does the energy become accessible. The wax vapor meets oxygen in the air and burns. Light and heat are released, and the process begins again. more wax melts, more liquid rises, more vapor forms. The flame continues, supported by the wax's willingness to change state slowly and predictably. This is why wax is such an effective fuel. It does not rush. It does not release energy all at once. It waits for heat, responds gradually, and feeds the flame at a controlled pace. Candle waxes come from many sources, but their role remains the same. Some waxes are refined from petroleum. Others are derived from plants or produced by insects. Regardless of origin, each wax used in candles is selected because it can store energy safely and release it gently. The differences between waxes are felt more in behavior than in appearance. Some burn longer, some melt more evenly, some hold fragrance more easily. Some cool into smooth surfaces, while others form subtle textures as they solidify again. As wax cools, it returns to stillness. When a candle is extinguished, the flame disappears, but the wax remains. The liquid pool slowly hardens. The molecular chains settle back into place. Energy stays stored, unchanged, waiting for the next moment of warmth. This ability to pause and resume is part of what makes a candle feel calm. Nothing is wasted. Nothing is hurried. The wax does not decay while it waits. It simply holds potential. Even the visible surface of a candle reflects this quiet behavior. Over time, small changes appear. A shallow well may form around the wick. The edges may remain untouched. These shapes tell the story of how the wax has melted and cooled again and again, always following the same gentle rules. Wax does not decide when to burn. It responds. It waits for heat. It changes when needed. And when the heat is gone, it rests. This patient relationship between wax and flame is what allows a candle to burn for hours without effort or noise. The wax does not resist the process, nor does it rush through it. It offers energy only as quickly as the system allows. In this way, candle wax is not just a material. It is a reservoir, a quiet store of energy, shaped to release itself slowly, one small change at a time. The wick is the quiet connector inside a candle. It does not glow brightly. It does not draw attention. Yet without it, the candle would remain still and unlit. At a glance, a wick appears simple, often just a thin strand rising from the center of the wax. But its role is precise. The wick exists to move fuel slowly, reliably, and in the correct amount. It is not there to burn away quickly or to hold a flame on its own. It is there to guide wax through the candle in a controlled way. When a candle is lit, the wick is the first part to respond. Heat from the flame travels downward along the wick, warming the wax that surrounds it. As the wax melts, the wick begins its main task, lifting the liquid upward. This movement happens through a process called capillary action. The wick is made of many small fibers twisted or braided together. Between these fibers are tiny spaces. Liquid wax naturally moves through these narrow spaces, climbing upward even against gravity. No pump is needed. The structure of the wick alone is enough. The wick does not pull wax quickly. It allows wax to rise gradually. This pace is essential. If too much liquid wax were delivered to the flame at once, the flame would grow too large, burn unevenly, or produce smoke. if too little wax reached the flame would weaken or go out. The wick acts as a regulator, determining how much fuel reaches the flame at any moment. Wicks are carefully designed to match the wax they are paired with. Thicker waxes require different wick structures than softer waxes. A wide candle needs a different wick than a narrow one. Even the way a wick is braided can change how it behaves. Some wicks are designed to curl slightly as they burn. This curling motion moves the tip of the wick toward the outer edge of the flame, where it is exposed to more oxygen and heat. As a result, the very end of the wick burns away gradually, trimming itself without intervention. This self-adjusting behavior helps keep the flame stable over time. If a wick is too thick, it may deliver more fuel than the flame can burn cleanly. This can cause the wick tip to form a small glowing clump, sometimes called a mushroom. If a wick is too thin, it may not lift enough wax, allowing melted wax to drown the flame. A well-matched wick avoids both extremes. The material of the wick also matters. Most modern candle wicks are made from cotton or cotton blends. These materials are chosen because they burn predictably and leave minimal residue. Some wicks include a small core made of paper or safe metals to help them remain upright as the wax melts around them. The wick itself does not provide much energy. It is not meant to be the main fuel. In fact, a properly functioning wick burns very slowly. Its purpose is not to disappear quickly, but to remain present long enough to guide wax upward hour after hour. As the candle burns down, the wick shortens, the wax level drops. Yet the relationship between wick and wax remains steady. The wick continues its work until there is no more wax to lift. Even when a candle flickers, the wick remains patient. Small drafts may cause the flame to lean or dance, but the wick continues feeding it at the same measured pace. When the air grows still again, the flame returns to its balanced shape. The wick does not react dramatically to change. It responds quietly. This steady behavior is one reason candles feel predictable and safe to watch. Nothing about the wick is sudden or aggressive. Its movements are invisible. Its work is constant. When a candle is extinguished, the wick remains in place. It darkens slightly where it has been exposed to heat, but it does not continue burning. The pathway closes. Wax cools. The system pauses. The next time the candle is lit, the wick resumes its role without hesitation. The wick does not store energy. It does not create energy. It simply moves energy from one place to another. In this way, the wick is less like a fuel source and more like a quiet road. A narrow passage through which wax travels, one slow step at a time, allowing the flame to exist calmly and continuously. Without the wick, a candle would have wax and heat, but no connection between them. With it, the candle becomes a complete system, balanced, patient, and steady in its behavior. The flame is the most visible part of a candle, yet it is also the most misunderstood. It appears simple, a small shape of light resting above the wick. But what the flame is actually doing is a continuous series of quiet actions, each one depending on the last. A candle flame is not a solid object. It is a moving process. At every moment, the flame is consuming wax vapor that rises from the wick. This vapor mixes with oxygen in the surrounding air, and together they react, releasing energy in the form of light and heat. The flame exists only as long as this exchange continues. The heat produced by the flame serves two purposes at once. Part of it radiates outward, warming the nearby air and surfaces. Another part travels downward, returning to the wax below. This returning heat is essential. Without it, the wax would not continue melting, and the flame would have nothing left to burn. In this way, the flame sustains itself by preparing its own fuel. The shape of the flame reflects this balance. Most candle flames taper toward the top and widen slightly near the middle. This shape forms because hot gases rise. As the wax vapor burns, the heated gases move upward, pulling fresh air in from the sides. The flame becomes a small, steady current, flowing upward rather than outward. The brightest part of the flame is often near its center. This light comes from tiny particles formed during combustion. These particles heat up and glow, producing the warm yellow light associated with candles. When conditions are just right, these particles burn away before leaving the flame, keeping the light clean and steady. If the balance shifts, the flame changes. When too much wax vapor reaches the flame at once, combustion becomes less complete. The flame may grow taller, flicker more, or release small amounts of smoke. When too little vapor is available, the flame shrinks, dims, or struggles to remain lit. Air movement plays an important role as well. A gentle flow of air can make the flame lean or sway, but it usually returns to its original shape once the air settles. Strong drafts, however, can disrupt the balance, cooling the flame or pulling fuel away before it can burn fully. This sensitivity is part of what makes candlelight feel alive. The flame is always adjusting, responding to tiny changes in temperature, fuel flow, and air movement. Yet these adjustments happen gradually. There are no sharp reactions, no sudden surges. The flame corrects itself in small increments, maintaining its presence through balance rather than force. The color of a candle flame also reflects what it is doing. The familiar yellow glow comes from glowing particles within the flame, while the faint blue region near the base marks an area where combustion is especially efficient. In this lower zone, wax vapor mixes more completely with oxygen, producing less visible light, but more concentrated heat. This layered structure exists even when it is difficult to see. The flame does not touch the solid wax directly. It remains slightly above the wick, suspended in a space where vapor and air meet. This separation allows the flame to burn without consuming the candle all at once. It creates distance, slowing the release of energy. Because of this, a candle does not behave like an open fire. It does not spread. It does not seek new fuel beyond what the wick provides. The flame stays where it is, anchored to the pathway beneath it. As time passes, the flame remains remarkably consistent. Minutes turn into hours, and the same quiet process repeats again and again. Wax melts, vapor forms, energy is released, heat returns downward. Even the soft sound sometimes heard from a candle, the faint hiss or whisper, is part of this process. It comes from gases moving and reacting, not from the flame itself making noise. Most of the time, the process is nearly silent. When the candle is extinguished, the flame disappears instantly. The reactions stop. The light vanishes, but the heat lingers briefly. The wick may glow faintly for a moment, releasing a thin trail of smoke as remaining vapor dissipates into the air. Then stillness returns, The flame does not struggle to exist, nor does it resist ending. It appears when conditions allow, and it fades when they do not. This acceptance of balance is part of what makes candlelight feel gentle rather than demanding. A candle flame is not aggressive. It does not rush. It responds. It exists as long as fuel, heat, and air meet in the right proportions. And when they no longer do, the flame rests, leaving behind a quiet warmth and the memory of light. Candlelight has a color that feels immediately familiar. It is soft, it is warm, and it is distinctly different from most modern light sources. This warm yellow glow is not an accident of tradition or design. It is a direct result of what is happening inside the flame, moment by moment, as wax vapor burns. Much of the light from a candle comes from tiny particles formed during combustion. As wax vapor rises from the wick and mixes with oxygen, it does not always burn perfectly cleanly. Instead, extremely small particles of carbon are created within the flame. These particles become intensely hot, and as they heat up, they begin to glow. This glowing is what produces the familiar yellow light. The particles are so small that they do not appear as smoke when combustion is balanced. They exist briefly inside the flame, glowing as they release energy, and then they burn away before leaving the flame. When this process remains steady, the light appears smooth and continuous. The brightness of a candle flame depends on how much wax vapor is available and how evenly it burns. When the flame receives the right amount of fuel, the glowing particles form and disappear in a stable rhythm. The flame looks calm, steady, and softly luminous. If more fuel arrives than the flame can process, the balance shifts. An overfed flame grows larger. The glowing particles increase in number, but not all of them burn away completely. Some escape the flame and appear as smoke or soot. The light may flicker more sharply, and dark residue can form on nearby surfaces. When less fuel is available, the opposite happens. The flame becomes smaller and dimmer. The glow weakens, and the light may appear thinner or less consistent. In extreme cases, the flame can fade out entirely. The warm color of candlelight is tied closely to this balance. Because the light comes from glowing particles rather than direct emission from excited gases, it contains more longer wavelengths. These longer wavelengths are perceived by the human eye as yellow and amber tones. This is why candlelight feels warmer than white or blue, leaning artificial lights. Many electric lights produce light by exciting atoms or using phosphors, which can create sharper, cooler colors. Candlelight, by contrast, comes from heat itself. It is light born from warmth. Despite differences in wax type, most candle flames look remarkably similar when they are well designed. Paraffin, soy, beeswax, and blended waxes all produce a familiar yellow flame when fuel delivery and airflow are balanced. The underlying behavior of the flame remains the same across these materials. What changes is not the color itself, but how easily that balance is maintained. A wax that delivers fuel smoothly supports a steady glow. A wax that melts unevenly or feeds the wick too quickly can push the flame out of its ideal range. This is why wick choice and wax formulation matter more than wax origin alone. When everything works together, the flame settles into a stable state. This stability is part of what makes candle flames so recognizable. Even at a distance, the soft, warm glow signals a slow-burning flame. The light does not pulse rapidly or shift color dramatically. It holds a consistent presence, changing only slightly as air currents move around it. The flame's movement is gentle because it is not being forced. The heat rises naturally. Fresh air is drawn in quietly from the sides. The glowing particles form and disappear in a continuous cycle. This calm behavior contrasts strongly with brighter flames, such as those from torches or open fires. Those flames burn hotter, faster, and with less restraint. Their light is more intense and often less stable. A candle flame is smaller by design. It releases energy slowly. It limits its own brightness. It remains anchored to the wick. This controlled release of light is part of why candles feel restful to watch. The flame provides enough visual interest to hold attention, but not so much that it overwhelms the senses. The glow invites observation without demanding it. Over time, the eyes adjust to candlelight. Shadows soften. Edges blur gently. The space around the flame feels quieter, as though the light itself is encouraging stillness. The warm yellow color of a candle is not just a visual trait. It is a sign that the flame is balanced, receiving fuel at the right pace, releasing energy evenly, and remaining stable in its behavior. It is the visible expression of a system working as intended. A small flame, a steady glow, and a quiet balance between heat and fuel, repeating itself without hurry. As a candle burns, one of the most important changes happens quietly at its surface. Solid wax gives way to liquid, forming a shallow pool around the wick. This pool may look simple, but it plays a central role in how the candle behaves. The melt pool is the candle's fuel reservoir. It is the place where solid wax becomes liquid, preparing itself for its slow journey upward through the wick. The size, shape, and temperature of this pool influence nearly every aspect of the burn, from flame stability to scent release. When a candle is first lit, the flame begins warming the wax directly around the wick. At first, the melted area is small. The pool is narrow and shallow. As time passes, heat spreads outward and the pool gradually widens. The rate at which this happens depends on several factors working together. Wax type matters. Wick thickness matters. Candle diameter matters. Some waxes melt easily and spread quickly, forming a smooth, even pool early in the burn. Others resist melting, holding their shape longer and creating a smaller pool for an extended time. Neither behavior is right or wrong. Each creates a different burning rhythm. In container candles, the melt pool plays an additional role. As the wax warms and liquefies, it releases fragrance compounds into the air. These compounds evaporate more readily when the wax reaches a certain temperature. If the pool is too cool, fragrance release remains subtle. If it becomes too hot, scent can be released too quickly and fade sooner over time. This is why many container candles are designed to form a full melt pool that reaches close to the edges of the vessel. An even pool helps distribute heat uniformly and allows fragrance to rise steadily rather than in bursts. The appearance of the melt pool can vary. Some waxes form clear, glass-like liquid surfaces. Others appear cloudy or milky when melted. These visual differences reflect the internal structure of the wax and how its molecules arrange themselves as they warm. As the candle continues burning, the melt pool remains in motion. Liquid wax is constantly being drawn upward through the wick, while new solid wax melts at the edges. This creates a gentle circulation within the pool, even though it may not be visible to the eye. When a candle is extinguished, the melt pool begins to cool. As the temperature drops, the liquid wax slowly returns to a solid state. During this cooling process, the wax contracts slightly. This contraction can create subtle visual effects, especially in container candles. Small gaps may form between the wax and the glass. These are often called wet spots. Wet spots do not affect how a candle burns. They are simply a result of wax pulling inward as it cools and shrinks. Because different waxes contract at different rates, some show these effects more than others. The surface of the cooled wax also tells a story. Smooth surfaces suggest even cooling. Slight ripples or textures may form if the wax cooled unevenly or was disturbed by air movement. These patterns are natural outcomes of the wax's behavior as it changes state. The size of the candle strongly influences how the melt pool behaves. A wide candle requires more heat to melt wax across its surface. To achieve this, it needs a wick capable of delivering enough fuel to sustain a broader flame. A narrow candle, by contrast, reaches its full melt pool more quickly with less heat. This balance between candle size and wick selection determines whether a candle burns evenly or forms a deep well around the wick. If the wick is too small for the candle's width, the melt pool may never reach the edges, leaving unused wax behind. If the wick is too large, the pool may become excessively deep or hot. A well-designed candle finds the middle ground. The melt pool grows at a controlled pace, reaches an appropriate width, and maintains a steady temperature. It feeds the wick without flooding it. It releases fragrance without rushing it. It remains present without drawing attention to itself. Watching a candle burn over time reveals this quiet consistency. The pool expands, holds, and recedes with a gentle rhythm. Nothing dramatic occurs. The process repeats with each lighting, following the same physical rules. The melt pool is not just a side effect of burning. It is an essential part of the candle's system. It connects the stillness of solid wax to the activity of the flame, acting as a buffer between storage and release. Liquid wax rests briefly in this pool before continuing its journey. It waits, warms, and then moves on, leaving behind only subtle traces of its passage. Paraffin wax is the most widely used candle wax in the modern world. It is familiar, consistent, and quietly reliable. While many people encounter paraffin candles without thinking much about the material itself, paraffin has played a central role in shaping what candles are today. Paraffin became widely available in the mid-1800s, at a time when people were searching for safer, cleaner, and more affordable lighting. Before paraffin, many candles were made from animal fats or beeswax. These materials worked, but they came with limitations. Tallow candles often smoked and carried strong odors. Beeswax burned more cleanly, but it was expensive and difficult to produce in large quantities. Paraffin offered an alternative. Refined from petroleum, paraffin wax could be produced consistently and in large volumes. Its properties were predictable, and its cost made candles more accessible to everyday households. As production methods improved, paraffin gradually became the dominant wax for candles across much of the world. One of paraffin's defining traits is its consistency. High-quality paraffin wax is purified to remove impurities that could interfere with burning. This purification allows the wax to melt, flow, and vaporize in a controlled way. When paired with an appropriate wick, paraffin can produce a steady flame with minimal smoke. Paraffin wax can also be manufactured with different melting points. This flexibility allows it to be tailored for different types of candles. Lower melting paraffin is often used for container candles, where smooth melting and fragrance release are important. Higher melting paraffin is used for pillars and tapers, where structural strength and slower melting are needed. Despite coming from a single source material, paraffin wax can behave very differently depending on how it is formulated. Another reason paraffin remains popular is its ability to hold fragrance. Many fragrance oils dissolve easily into paraffin, allowing scent to be distributed evenly throughout the wax. When the candle burns, these fragrance molecules are released gradually as the wax warms. This makes paraffin especially effective for scented candles designed to fill a space with a consistent aroma. Paraffin also responds well to additives. Small amounts of other materials can be blended into the wax to adjust hardness, appearance, or burning behavior. These adjustments allow manufacturers to fine-tune candles for specific purposes, such as improving surface smoothness or reducing visual imperfections as the wax cools. Visually, paraffin wax often appears translucent or slightly glossy when solid. When melted, it forms a clear pool that reflects light easily. This clarity contributes to the bright, steady appearance of paraffin candle flames and helps the glow travel through the wax itself. Because paraffin melts and resolidifies smoothly, it supports repeated use. A candle can be burned, extinguished, cooled, and relit many times, each time returning to a familiar state. The wax does not degrade quickly simply from sitting or cooling. It remains stable until heat invites it to change again. Although paraffin is sometimes contrasted with plant-based waxes, its behavior in a candle follows the same fundamental rules. It stores energy in solid form, melts when heated, travels through the wick, and burns as vapor. The differences lie not in the process, but in how easily and consistently that process unfolds. In well-engineered candles, paraffin flames often appear calm and predictable. The wax delivers fuel at a steady pace. The wick remains well fed without being overwhelmed. The flame settles into balance, holding its shape and color for long periods of time. This predictability is part of paraffin's quiet appeal. It allows candle makers to design candles that behave the same way from one batch to the next. It allows users to know what to expect when a candle is lit. There are few surprises. Over time, paraffin has become a reference point. Other waxes are often described in relation to it: burning slower than paraffin, melting cooler than paraffin, or holding scent differently than paraffin. This comparison exists because paraffin established a reliable baseline. Paraffin is not dramatic. It does not draw attention to itself. It simply performs its role. In the context of a candle, paraffin acts as a dependable fuel source, shaped by refinement and repetition. It waits patiently in solid form, responds smoothly to heat, and releases its energy in a measured, familiar way. For more than a century, This quiet reliability has allowed paraffin to remain at the center of candle making, supporting countless small flames, one steady glow at a time. Soy wax entered the candle world much later than paraffin, but it has become a familiar presence in a relatively short amount of time. Its rise is closely tied to changes in manufacturing, consumer preference, and how people think about everyday materials. Soy wax is made from soybean oil. The oil is processed and hydrogenated, a step that changes it from a liquid into a solid wax at room temperature. This transformation gives soy wax the structure needed to hold a wick and burn slowly, while still allowing it to melt gently when heat is applied. In its solid form, soy wax often appears soft and opaque. Unlike paraffin, which can look slightly translucent, soy wax has a creamy, matte appearance. This visual quality remains even as the candle ages, giving soy candles a distinct look that many people recognize immediately. One of soy wax's defining characteristics is its lower melting point. It begins to soften and melt at relatively gentle temperatures. This allows soy candles to form melt pools slowly and evenly, often creating a wide, shallow pool rather than a deep one. The flame does not need to work as hard to keep fuel flowing. Because of this, soy candles often burn at a slightly cooler temperature than paraffin candles. The flame may appear similar in size and color, but the overall heat output tends to be lower. This can contribute to a longer burn time, as fuel is released more gradually. The slower pace of a soy candle's burn is part of its appeal. The wax responds gently to heat, melting in a controlled way and feeding the wick without rushing. The candle settles into its rhythm and maintains it with little variation. Soy wax interacts with fragrance differently than paraffin. It can hold scent effectively, but there are limits to how much fragrance oil it can absorb while still burning cleanly. In many formulations, soy wax performs best with moderate fragrance levels. When overloaded, the wax may struggle to release scent evenly or may affect flame stability. To address this, soy wax is often blended with other waxes. Small amounts of paraffin or coconut wax are commonly added to improve fragrance distribution, adhesion to containers, or surface appearance. These blends retain many of soy wax's gentle burning qualities while enhancing performance. As soy wax melts, its liquid form often appears cloudy rather than clear. This cloudiness comes from the structure of the wax molecules and how they arrange themselves as they warm. It does not affect how the candle burns. It is simply a visual trait that distinguishes soy from other waxes. When a soy candle is extinguished, the wax cools and solidifies slowly. The surface may return to a smooth finish, or it may develop subtle texture depending on how evenly it cools. These patterns reflect the wax's softness and its sensitivity to temperature changes. Soy wax is also responsive to its environment. Changes in room temperature, air movement, or container material can influence how the wax behaves. A soy candle burning in a cool room may form its melt pool more slowly than one in a warmer space. These differences are gradual and do not disrupt the candle's overall function. Despite being plant-based, soy wax follows the same basic principles as any candle wax. It stores energy in solid form. It melts when warmed. It travels upward through the wick. It burns only after becoming vapor. The origin of the wax does not change the fundamental process. What soy wax offers is a different texture, a softer response to heat, and a slightly altered rhythm. The flame remains familiar, but the way the wax feeds it feels more relaxed. The melt pool spreads gently. The surface cools quietly. Over time, soy wax has found its place as an alternative rather than a replacement. It provides candle makers with another option, one that behaves differently but still fits comfortably within the same system. It expands the range of possible candle experiences without changing the core mechanics. Soy wax does not aim to outperform other waxes in every way. Instead, it offers balance. It brings a softer appearance, a slower burn, and a calm interaction with heat. Like all candle waxes, soy wax waits patiently until the moment it is warmed. When that moment arrives, it responds without urgency, releasing its stored energy one small change at a time, allowing the flame to exist gently above it. Beeswax is one of the oldest candle materials used by humans. Long before modern refining methods existed, beeswax was already valued for how cleanly and steadily it could burn. Its presence in candle history stretches back centuries, shaped by both natural processes and careful observation. Beeswax is produced by honeybees. Worker bees secrete wax from special glands and use it to build the structure of the honeycomb. This wax is not a single substance, but a complex mixture of natural compounds. Its chemical structure is dense and tightly packed, giving beeswax a firmness that many other waxes do not have. Because of this density, beeswax melts at a higher temperature than most common candle waxes. It typically softens and melts only after reaching relatively warm conditions. This higher melting point means that beeswax holds its shape well when solid, resisting deformation and remaining stable even in warmer environments. When heat is finally applied, beeswax responds slowly. As the flame warms the wax near the wick, the beeswax begins to melt in a controlled way. The melt pool tends to be smaller and deeper than that of softer waxes. Liquid beeswax moves upward through the wick at a measured pace, feeding the flame without rushing. This slow delivery of fuel contributes to beeswax's reputation for clean burning. Because the wax vapor reaches the flame gradually, combustion remains balanced. The flame often appears steady and bright, producing relatively little smoke when properly matched with an appropriate wick. Historically, this behavior made beeswax especially valuable. In times when indoor lighting relied entirely on open flames, smoke mattered. Tallow candles, made from animal fat, were common, but often produced strong odors and visible soot. Beeswax candles, by contrast, burned more cleanly and with a more pleasant scent. For this reason, beeswax candles were often reserved for important spaces. In medieval Europe, they were commonly associated with churches and other formal settings. Their clean light and minimal smoke made them suitable for enclosed interiors where air circulation was limited. Beeswax also carries a natural aroma. When warmed, it can release a faint, gentle scent, often described as honey-like or floral. This scent does not come from added fragrance oils, but from the wax itself. It is subtle and usually remains close to the flame, rather than filling a room. The color of beeswax varies naturally. It can range from pale yellow to deep golden tones, depending on how it was processed and what the bees encountered while producing it. These natural colors remain visible in both solid and melted forms, contributing to beeswax's distinctive appearance. Because beeswax is firmer and more viscous when melted, it often requires a larger or sturdier wick. Square-braided wicks have traditionally been used with beeswax because they can support the thicker liquid wax and maintain a steady fuel flow. This pairing helps prevent the flame from becoming starved or overwhelmed. As a beeswax candle burns, it changes slowly. The wax near the wick melts, travels upward, and burns as vapor, while the surrounding wax remains solid. The candle retains its shape longer than softer wax candles, gradually narrowing rather than forming wide melt pools. When extinguished, the beeswax cools and solidifies again, returning to its firm state. The surface may appear smooth or slightly textured, reflecting how the wax settled as it cooled. These changes are natural and do not affect how the candle functions the next time it is lit. Despite its age, beeswax follows the same fundamental rules as all candle waxes. It stores energy in solid form. It melts when heated. It travels through the wick. It burns only after becoming vapor. What distinguishes beeswax is the pace at which these changes occur. Everything happens a little more slowly. The wax resists melting. The fuel rises deliberately. The flame remains steady. Beeswax does not try to adapt itself to modern expectations. It behaves according to its natural structure, shaped by biology, rather than industrial refinement. This gives beeswax candles a quiet presence, rooted in long-standing patterns. Even today, beeswax remains recognizable. Its weight, texture, and scent set it apart. It represents an earlier chapter in candle making, one where material properties were discovered through use rather than engineered through design. Yet when lit, a beeswax candle performs the same calm work as any other candle. It releases stored energy slowly, maintaining a small, steady flame that exists comfortably within its limits. Old, dense, and naturally aromatic, beeswax continues to offer light in the same measured way it always has, one quiet burn at a time. Beyond soy wax, there is a quiet range of other plant-based waxes used in candle making. These waxes come from different crops, climates, and processing methods, yet they all serve the same basic purpose: to store energy in solid form and release it slowly through heat. Each plant wax brings its own texture, melting behavior, and visual character. The differences are subtle, but they shape how a candle looks, feels, and burns over time. Palm wax is one of the most visually distinctive plant waxes. When it cools, palm wax can form crystalline patterns that spread across the surface. These patterns often resemble feathers, frost, or delicate branching structures. They are not decorative additives, but natural formations created as the wax solidifies and its molecules arrange themselves. Palm wax is relatively firm compared to soy. It holds its shape well and can support candles that remain upright without containers. When heated, palm wax melts more slowly than softer plant waxes, forming a controlled melt pool that feeds the flame steadily. The crystalline patterns may fade when the wax melts and then reappear as it cools again. Coconut wax is very different in character. It is one of the softest plant waxes used in candles. At room temperature, it can feel almost creamy to the touch. Because of this softness, coconut wax is rarely used on its own. Instead, it is commonly blended with other waxes. In blends, coconut wax contributes smoothness and flexibility. It helps wax adhere evenly to containers and can improve surface appearance after cooling. Coconut wax also melts easily, allowing candles to form melt pools with gentle heat. This can support slow, even fragrance release when used in scented candles. Rapeseed wax, also known as canola wax, is another plant-based option used widely in some regions, particularly in parts of Europe. Like soy, it is derived from a common agricultural crop and processed into a solid wax through hydrogenation. Rapeseed wax tends to have a smooth, matte appearance and a moderate melting point. When used in candles, rapeseed wax melts evenly and feeds the wick at a steady pace. Its behavior is often described as balanced, neither as firm as palm wax nor as soft as coconut wax. This middle ground makes it suitable for container candles and blends designed for consistent burning. Despite these differences in appearance and handling, plant waxes share the same basic combustion behavior. None of them burn in solid form. All must melt, travel through the wick, and become vapor before releasing energy. The flame does not distinguish between plant-based wax and other waxes. It responds only to how fuel is delivered. What changes is how easily that delivery occurs. A firmer wax resists melting and releases fuel more slowly. A softer wax melts readily and offers fuel more quickly. Blends are often used to fine-tune this balance. Plant waxes are often chosen for their texture and behavior, rather than their origin alone. Some create smoother surfaces after cooling. Others form patterns. Some support wide melt pools, while others maintain narrower ones. Candle makers adjust wick size and formulation to match these traits. As plant wax candles burn, their surfaces tell a quiet story. The melt pool forms, spreads, and recedes. Crystalline patterns soften and return. Opaque wax becomes translucent when warmed, then cloudy again as it cools. These visual changes happen slowly, without drama. When extinguished, plant wax candles return to stillness. The wax cools, contracts slightly, and settles back into place. Small variations in texture may appear, reflecting the wax's response to temperature and time. These changes do not interfere with future burns. They are simply part of the material's rhythm. Discussions around plant waxes often include considerations of sourcing and sustainability. Different crops require different growing conditions, and their impacts vary by region and practice. These factors influence how plant waxes are produced and where they are used, but they do not alter the physical behavior of the candle itself. In the flame, all waxes behave according to the same quiet rules. Plant waxes do not transform candle making. They expand it. They add new textures, new melting behaviors, and new visual qualities, while remaining part of the same fundamental system. The candle still relies on balance between heat and fuel, between solid and liquid, between storage and release. These waxes offer variety without disruption. They allow the candle to remain what it has always been, a slow, controlled source of light, shaped gently by the material beneath the flame. In this way, plant waxes beyond soy contribute subtle differences rather than dramatic change. They wait patiently, respond to warmth, and release energy only as the system allows. Some candles are designed to blend into their surroundings. Others are designed to be noticed. Gel wax candles belong to the second group. They are often clear or translucent, revealing objects embedded inside the wax, shells, glass pieces, stones, or decorative shapes suspended in place. At first glance, these candles may seem very different from traditional wax candles, but beneath their appearance, the same quiet principles still apply. Gel wax is typically made from a combination of mineral oil and a polymer that thickens it into a clear, jelly-like substance. When cool, gel wax holds its shape while remaining transparent. When heated, it softens and flows, much like other candle waxes, though often at a different pace. The clarity of gel wax is its defining feature. Unlike paraffin or soy, which appear opaque or cloudy, gel wax allows light to pass through it easily. When a flame burns above it, the wax can glow from within, illuminating embedded objects and creating layered reflections. Despite this visual difference, gel wax does not burn in solid form. Like all candle fuels, it must first warm, then change, then release vapor. The flame consumes vaporized fuel above the wick, not the gel itself. Gel wax often burns at a lower temperature than firmer waxes. This slower heat release allows the wax to remain clear for longer periods and helps maintain the integrity of the objects inside. Because of this, gel candles usually rely on specially selected wicks that can lift the thicker fuel at a controlled rate. Wick choice is especially important in gel candles. A wick that delivers too much fuel can cause the flame to grow too large or overheat the wax. A wick that delivers too little fuel may struggle to stay lit. The balance must be precise, as gel wax behaves differently from solid wax blends. Many gel candles are created primarily for visual effect, rather than extended burn performance. Their appeal comes from appearance, not from how long they last or how evenly they melt. The embedded objects remain fixed, while the gel slowly recedes as fuel is consumed. These candles are often referred to as novelty candles because their purpose is not only to provide light, but to create interest. The flame becomes part of a larger display, interacting with what surrounds it. Light refracts through the gel, softening edges and adding depth. Even in these visually focused designs, the flame remains governed by the same limits. It cannot exceed the rate at which fuel is delivered. It cannot burn without oxygen. It cannot exist without heat returning downward to sustain the process. As gel wax warms, it may develop subtle movement within its body. Small currents can form as warmer material rises and cooler material settles. These motions are gentle and slow, visible only when the candle is observed closely. When extinguished, gel wax cools and becomes still again. The surface smooths, the clarity returns. The objects remain suspended exactly where they were placed, unchanged by the brief release of energy. Some novelty candles combine gel wax with traditional wax layers. A candle may have a solid wax base with a clear gel top, blending stability with visual transparency. These hybrid designs still rely on careful engineering to ensure that fuel delivery remains balanced. The presence of decorative objects does not change how combustion works, but it does change how heat spreads through the wax. Materials inside the gel may absorb or reflect heat differently, influencing how the wax melts nearby. For this reason, novelty candles require careful design to remain stable and predictable. Despite their decorative focus, gel candles still express the same calm rhythm when properly made. The flame remains small and controlled. The wax responds slowly. The system holds itself together through balance. Gel candles remind us that a candle does not need to be plain to follow simple rules. Even when designed for visual interest, the candle remains a system of fuel, heat, and air working together quietly. In the end, novelty candles are not exceptions. They are variations. Their transparency and decoration change how we see the flame, but not how the flame behaves. The light still rises gently. The fuel still arrives slowly. The process remains patient. Even when a candle is made to be looked at, it still burns according to the same steady principles, releasing energy gradually, then returning to stillness when the flame is gone. Many modern candles are not made from a single type of wax. Instead, they are carefully blended. This blending is not about complexity for its own sake. It exists because no single wax naturally provides every quality a candle needs. Each wax has strengths, and each has limits. Some waxes are firm and hold their shape well, but melt slowly. Others melt easily, but may be too soft to support certain candle styles. Some hold fragrance efficiently, while others release scent more gently. Rather than choosing one quality and accepting the rest, candle makers combine waxes to create balance. A blend allows the candle to behave in a more controlled way. By adjusting the proportions of different waxes, candle makers can fine-tune how a candle responds to heat. The melting point can be raised or lowered. The hardness of the solid wax can be adjusted. The speed at which fuel reaches the flame can be moderated. This tuning affects how the candle looks, how it burns, and how it feels over time. Paraffin soy blends are among the most common. Paraffin contributes consistency and reliable fuel delivery. Soy adds softness and a gentler melting behavior. Together, they create a wax that forms smooth melt pools, supports steady fragrance release, and cools with minimal surface disruption. Soy coconut blends are another example. Soy provides structure, while coconut wax adds creaminess and flexibility. This combination can improve how wax adheres to containers and how evenly it cools after being extinguished. Blending is also used to control how wax responds as it cools. Some waxes shrink more than others. When blended carefully, these tendencies can offset each other, reducing visible gaps or uneven surfaces. The goal is not perfection, but predictability. One of the oldest blending techniques involves stearic acid, also known as stearin. This material has been used in candle making since the 19th century. When added to paraffin, stearin increases hardness and raises the melting point. This makes the wax better suited for pillars and tapers, which need to remain upright and burn without collapsing. Stearin also affects how wax crystals form as the candle cools, influencing surface appearance and opacity. These changes are subtle, but they contribute to how the candle feels in use. Blends are also designed around the candle's environment. A container candle behaves differently than a freestanding candle. Glass holds heat. Metal reflects it. Open air cools wax more quickly than enclosed spaces. By blending waxes, candle makers adjust how heat spreads through the candle and how fuel is delivered to the flame. This is why strong candle performance does not come from a single ingredient. It comes from the system. Wax, wick, and vessel work together. A well-chosen blend supports the wick by delivering fuel at the right pace. The wick, in turn, supports the flame by lifting fuel without excess. The vessel shapes how heat is retained or released. If any part is mismatched, the system loses balance. Blends allow this balance to be refined. No wax is perfect on its own because candles are asked to do many things at once. They must remain solid at room temperature. They must melt predictably when heated. They must deliver fuel without flooding. They must cool without cracking or pulling away too dramatically. They must release fragrance without overwhelming the flame. Blending makes these competing needs easier to meet. When a candle burns smoothly, it can be tempting to assume simplicity. But behind that smooth burn is a series of choices. Small adjustments in wax composition can change how long a candle lasts, how evenly it burns, and how stable the flame appears. These adjustments are not visible once the candle is finished. The blend does not announce itself. It simply does its work quietly. As the candle burns, the blended wax melts into a unified pool. The individual components are no longer distinct. They behave as one material, responding to heat in a coordinated way. Fuel rises steadily. The flame remains calm. When the candle is extinguished, the blend cools and settles back into solid form. Any differences in melting point or texture are resolved during cooling. The wax becomes still again, ready for the next lighting. Candle blends exist because candles ask for balance. They are shaped by compromise rather than extremes. By combining waxes, candle makers create materials that behave gently under heat, remain stable over time, and support the flame without drawing attention to themselves. In the end, a blend is not about mixing for variety. It is about harmony. In candle making, not every important ingredient is meant to be noticed. Some materials are added in very small amounts, not to change what a candle is, but to help it behave more smoothly. These materials are called additives, and their role is quiet, but important. Additives do not provide fuel. They do not create light. They simply help the wax and flame work together more reliably. One of the oldest additives used in candle making is stearin, also known as stearic acid. This substance has been used since the 19th century to adjust the properties of wax. When added to paraffin, stearin increases hardness and raises the melting point. This makes the wax more suitable for candles that need to stand upright, such as pillars and tapers. Stearin also influences how wax crystals form as the candle cools. It can make the surface appear more opaque and reduce certain visual irregularities. These effects are subtle, but they contribute to a candle's stability and appearance over time. Another commonly used additive is a polymer known as fiber. Fiber is added in very small quantities, often less than a few % of the total wax. Its primary role is to help wax hold fragrance oils more effectively. Fragrance oils can separate from wax if the wax cannot absorb them fully. Fiber helps bind these oils within the wax, allowing scent to remain evenly distributed. This improves how fragrance is released as the candle warms and prevents oil from pooling or leaking. Vybar can also increase wax opacity and slightly adjust hardness. These secondary effects help improve surface appearance and consistency, especially in container candles. Some additives are used to protect a candle's appearance over time. Ultraviolet light, including sunlight and certain indoor lighting, can cause dyes in wax to fade. UV stabilizers are added to slow this process. They absorb or block some of the energy that would otherwise alter the color molecules in the wax. These stabilizers do not affect how the candle burns. Their purpose is visual. They help a candle look the same weeks or months after it is made as it did when it was first poured. Microcrystalline wax is another additive, sometimes blended with paraffin. It differs from standard paraffin in its structure. Microcrystalline wax is more flexible and pliable, allowing it to smooth out brittleness. When added in small amounts, it can make wax less likely to crack or crumble, especially in cooler environments. This flexibility helps candles maintain their shape during handling and temperature changes. The wax becomes slightly more forgiving, without becoming soft or unstable. Additives are chosen carefully because they can influence how wax melts and cools. Even small amounts can change how fuel flows to the wick or how heat spreads through the candle. For this reason, additives are used sparingly and with specific goals in mind. Each additive addresses a particular challenge. One may help with hardness, another with fragrance retention, another with color stability. Rather than solving every issue at once, additives provide targeted support. They allow candle makers to fine-tune behavior without redesigning the entire wax blend. Despite their importance, additives remain invisible once the candle is finished. They do not announce their presence when the candle is lit. They do not change the shape of the flame or the nature of the light in obvious ways. Their influence is felt through consistency. A candle that burns evenly from start to finish. A surface that cools smoothly. A scent that releases gently rather than all at once. These outcomes are often the result of small adjustments rather than major changes. When a candle burns, the additives melt and move with the wax. They become part of the liquid pool, participating in the same cycle of warming and cooling. As the candle is extinguished, they return to stillness with the rest of the wax. Additives do not make candles more dramatic. They make them more reliable. They help the candle remain balanced even as conditions change. They support the system without drawing attention to themselves. In this way, additives are quiet helpers. They work behind the scenes, ensuring that the candle behaves as expected, releasing its energy slowly and steadily. Their presence is subtle, but without them, many modern candles would be less stable, less predictable, and less calm. Small additions, careful adjustments, and a smoother burn achieved quietly, one flame at a time. Most candle flames you encounter are supported by cotton wicks. They are quiet, familiar, and carefully designed to behave in a predictable way. While they may appear simple, cotton wicks are engineered to manage fuel delivery, flame height, and long-term stability. A cotton wick is made from many fine fibers twisted or braided together. These fibers create narrow channels that allow melted wax to rise steadily toward the flame. This movement happens continuously while the candle is burning, supplying fuel at a controlled pace. One of the most important qualities of modern cotton wicks is their ability to adjust themselves as they burn. This behavior is often described as self-trimming. As a cotton wick burns, the exposed portion gradually shortens. At the same time, the structure of the wick encourages it to bend or curl slightly. This curl moves the tip of the wick away from the center of the flame and toward its outer edge, where heat and oxygen are greater. In this position, the very end of the wick burns away more efficiently. This process helps prevent the wick from growing too long. If the wick were to remain upright and untrimmed, it could deliver too much fuel to the flame. The flame would grow taller, burn hotter, and potentially produce smoke or soot. Self-trimming behavior keeps the flame within a comfortable range. When the wick curls and trims itself gradually, fuel delivery remains balanced. The flame stays steady. The light remains soft. The system continues without interruption. If a wick is not well matched to the candle, this balance can be lost. A wick that is too thick may deliver more fuel than the flame can consume. In this case, the tip of the wick can develop a small dark clump. This clump is often called mushrooming. Mushrooming occurs when carbon particles collect at the end of the wick faster than they can burn away. While this does not mean the candle is unsafe, it can lead to larger flames and increased smoke if left unchecked. A wick that is too thin creates a different problem. If it cannot lift enough liquid wax, the flame may struggle to stay lit. Melted wax can accumulate around the wick, cooling it and reducing vapor formation. In some cases, the flame may flicker weakly or go out entirely. The goal is balance. Wick design plays a large role in achieving this balance. The tightness of the braid, the thickness of the fibers, and the overall diameter of the wick all affect how wax moves upward. Even small changes in structure can influence capillary flow. Modern cotton wicks are produced with these factors in mind. Many are flat braided rather than round. This shape encourages consistent curling behavior as the wick burns. The curl is not random. It is part of the design. Older candle wicks often required frequent trimming by hand to maintain a stable flame. As wick technology improved, self-trimming designs reduced the need for constant attention. The candle could burn more evenly on its own, adjusting gradually rather than abruptly. Despite this advancement, cotton wicks still respond to their environment. Air movement can influence how the wick burns. A draft may cause the flame to lean, changing how the wick curls. Once the air settles, the wick resumes its usual behavior. The wax itself also affects the wick. Softer waxes may deliver fuel more quickly, requiring a wick that trims itself efficiently. Firmer waxes may need a wick that resists curling too aggressively. Matching wick and wax remains an essential part of candle design. As a candle burns lower, the wick shortens naturally. The distance between the flame and the wax surface changes, but the wick continues lifting fuel as long as liquid wax remains available. This adaptability allows the candle to burn consistently from beginning to end. When the candle is extinguished, the wick cools and becomes still. It darkens slightly at the tip, bearing a small record of its work. The pathway closes. The flame disappears. The system pauses. When relit, The wick resumes its role without delay. The curl returns. The trimming continues. The flame settles back into balance. Cotton wicks do not seek attention. They do not create light on their own. They simply manage the flow. Through careful design, they allow a candle to maintain a steady flame without constant adjustment. They help the candle remain calm, predictable, and quiet in its behavior. The soft glow above the wick depends on this subtle work. And though the wick itself is small, its influence shapes every moment the candle burns. Wood wicks offer a different experience from traditional cotton wicks. They change not only how a candle looks, but how it feels in a room. While the flame remains small and controlled, the presence of sound and the shape of the light introduce a new layer of quiet attention. A wood wick is typically made from a thin strip of natural wood. Sometimes a single strip is used. Other times, 2 or more layers are bonded together to adjust how fuel is delivered. The grain of the wood runs vertically, guiding melted wax upward toward the flame. Like cotton wicks, wood wicks rely on capillary action. Melted wax travels through tiny channels in the wood structure, rising slowly toward the heat. This movement is steady, but the path is broader than that of a braided fiber wick. As a result, wood wicks often produce a wider flame. Instead of a narrow teardrop shape, the flame may appear flatter and more horizontal, stretching gently across the top of the wick. This broader flame spreads heat across a larger area of wax, which can influence how the melt pool forms. The sound associated with wood wicks comes from the way the wood reacts to heat. As the flame warms the wick, small amounts of moisture and trapped gases inside the wood are released. These releases create tiny pops and crackles. The sound is usually subtle, especially in a quiet room. It is not constant. It is not loud. It comes and goes softly. This irregularity contributes to the calming quality of the sound. Unlike repetitive mechanical noise, the crackle does not follow a strict pattern. Each small sound is slightly different from the last, blending naturally into the background. Wood wicks became especially popular in the early 2000s as candles shifted from purely functional objects to ambient ones. The gentle crackle reminded many people of fireplaces, campfires, or burning logs, even though the scale was much smaller. This association added emotional texture without increasing brightness or heat. Because wood wicks deliver fuel across a wider surface, they must be carefully sized. A wick that is too wide can deliver more fuel than the flame can process cleanly. This may lead to excess smoke or soot. A wick that is too narrow may struggle to stay lit, especially if the wax is firm or slow to melt. Matching the wick to the wax is especially important with wood wicks. Softer waxes may flow easily and support wide flames. Firmer waxes may require layered or reinforced wicks to maintain steady fuel delivery. The vessel also matters. A container that holds heat can help a wood wick remain stable. In open air, heat disperses more quickly, which may affect how evenly the wick burns. When everything is balanced, the flame settles into a calm, wide glow. The melt pool spreads evenly. The sound remains occasional and gentle. The candle holds its presence without drawing too much attention to itself. The light produced by a wood wick flame often feels softer, not because it is dimmer, but because it spreads differently. The broader flame creates a wider area of illumination close to the candle, reducing sharp contrasts. Shadows appear more diffuse. As the candle burns, the wood wick gradually shortens. The edges of the wood char and darken. The flame continues feeding on vaporized wax rather than the wood itself. The wick's role is still to deliver fuel, not to be consumed rapidly. When the candle is extinguished, the sound stops immediately. The flame disappears. The wood cools and becomes still. Any remaining warmth dissipates quietly into the surrounding air. Over repeated burns, the wick's surface changes slowly. The charred area grows, but the underlying structure remains intact as long as wax continues to supply fuel. This gradual change does not interrupt the candle's rhythm. Wood wicks do not replace cotton wicks. They offer an alternative. They add sound without noise. They add width without intensity. They add texture without complexity. For those who notice them, wood wicks create a small, self-contained environment. Light, heat, and sound combine into a gentle experience that remains slow and controlled. Even with these added sensory elements, the candle remains what it has always been: a system of balance, a steady exchange of fuel and heat, a quiet release of energy shaped by material and design. Candles are often thought of as silent. Most of the time they are. Yet when a candle produces sound, even softly, it can change the feeling of a space. A faint crackle or whisper becomes part of the atmosphere, blending with the glow of the flame and the stillness of the room. These sounds are usually subtle. They are easiest to notice when everything else is quiet. In a calm environment, even the smallest noise can stand out, not as a distraction, but as a gentle presence. Wood wick candles are the most common source of candle sound. As the wick warms, tiny amounts of moisture and trapped gases within the wood are released. These releases create small pops and crackles. Each sound is brief and irregular, never following a strict rhythm. This irregularity matters. The human brain responds differently to predictable sounds than to unpredictable ones. Repetitive, mechanical noises often draw attention and can become irritating over time. Soft, irregular sounds, by contrast, tend to fade into the background. They provide texture without demanding focus. Candle crackle falls into this second category. The sound is not loud enough to interrupt thought. It is not sharp enough to startle. It comes and goes gently. This makes it easy for the mind to accept the sound as part of the environment, rather than something to react to. Over time, the brain may stop actively listening, allowing the sound to blend into a sense of quiet. In addition to sound, the visual flicker of the flame contributes to the feeling of comfort. The flame moves slightly, responding to air currents and fuel flow. This movement is slow and continuous, without sudden changes. The combination of soft sound and gentle motion creates a small, contained sensory experience. Together, these elements form what can be described as a microenvironment. Within this space, light, sound, and warmth exist in balance. Nothing dominates. Each element supports the others without overwhelming the senses. Many people associate candle sounds with fireplaces. Even though a candle is much smaller, the soft crackle can trigger familiar memories. Fireplaces have long been linked with shelter, warmth, and rest. The mind recognizes the pattern, even when the scale is reduced. This association does not need to be conscious to have an effect. The brain is skilled at connecting sensory cues with past experiences. A faint crackle may recall evenings spent indoors, protected from the cold, or quiet moments shared in warm spaces. These associations can create a feeling of safety without any effort. Regular cotton wick candles are usually silent, aside from rare hisses or soft sputters when air or moisture escapes. Even these sounds, when they occur, are brief and gentle. They do not repeat often enough to become intrusive. In silence, these small sounds can feel meaningful simply because they are rare. The absence of constant noise allows the candle to define the soundscape. The room becomes quieter, and the listener becomes more aware of subtle changes. Breathing slows, attention softens. This shift does not require intention. It happens naturally when the environment provides few demands. Candle sounds are also limited by design. They are never amplified. They do not increase in volume over time. They remain close to the flame, fading quickly with distance. This containment helps keep the experience calm. The sound does not fill the room. It stays near its source. As the candle burns, the sound may change slightly. A new crackle appears. A pause follows. The rhythm remains loose and unstructured. There is no pattern to anticipate. This lack of expectation allows the mind to rest. When the candle is extinguished, the sound stops immediately. There is no lingering echo. The quiet returns without effort. The transition is smooth, not abrupt. This gentle ending reinforces the sense of calm rather than breaking it. Candle sounds feel cozy because they do not compete with attention. They exist alongside stillness, adding warmth without requiring engagement. They suggest presence without intrusion. Light flickers, sound whispers, heat radiates softly. Together, these elements create a sense of enclosure, even in open space. The candle becomes a small anchor point, grounding the environment without drawing focus away from rest. In the end, candle sounds are comforting, not because they are loud or impressive, but because they are restrained. They remind us that not all experiences need to be constant or intense to be felt. Sometimes, the smallest sounds are enough to make a space feel complete. As evening approaches, the human body begins to respond to changes in light. Brightness fades, colors soften, and the nervous system slowly shifts toward rest. Candlelight fits naturally into this transition because it is very dim compared to most modern lighting. Even a single overhead room light can produce hundreds of lux, a unit used to measure light intensity. A candle, by contrast, produces only a small amount of illumination. At about 1 meter away, candlelight is often measured at roughly 10 lux or less. This difference is significant. Low light levels send a clear signal to the brain that daytime activity is ending. The eyes relay this information to internal systems that help regulate sleep timing. Brighter light encourages alertness. Dimmer light allows the body to begin slowing down. In addition to being dim, candlelight has a distinct color profile. The light emitted by a candle contains very little of the shorter wavelengths, often described as blue or cool light. These shorter wavelengths are especially effective at suppressing melatonin, a hormone involved in preparing the body for sleep. Candlelight is dominated by longer wavelengths, warm yellows and ambers. These wavelengths have a much gentler effect on nighttime biology. They do not strongly signal wakefulness in the way bright white or blue-leaning lights do. This is one reason candlelight often feels less intrusive in the evening. Modern lighting, particularly LEDs and screens, is designed for clarity and brightness. Phones, tablets, and televisions emit light that is rich in short wavelengths. Even at moderate brightness levels, this kind of light can stimulate the brain and delay the feeling of sleepiness. Candlelight behaves differently. It illuminates only a small area. Shadows remain soft. Details fade quickly with distance. The eyes do not need to adjust constantly. This reduces visual demand and allows attention to settle. The combination of low intensity and warm color creates an environment that feels naturally suited to winding down. The brain does not receive strong signals to remain alert. Instead, it is allowed to drift toward a quieter state. For this reason, candlelight can function as a circadian-friendly pre-sleep ambience when used thoughtfully. It can mark the transition between active evening tasks and rest. Lighting a candle may become a gentle cue that the day is ending. This cue does not rely on brightness. It relies on contrast. Against the surrounding darkness, the candle provides just enough light to feel present without dominating the space. The environment feels contained rather than exposed. However, candlelight must be understood as an atmosphere, not a sleep aid on its own. It supports rest by reducing stimulation, not by causing sleep directly. The body still responds to routine, timing, and overall environment. Safety remains an important consideration. While candlelight can be calming, candles should never be left burning unattended. They should be extinguished before sleep begins. The calming effect comes from the light and the atmosphere created beforehand, not from the candle burning throughout the night. Extinguishing the candle becomes part of the ritual. Light fades. The room darkens further. Stillness increases. This gentle ending reinforces the body's movement toward rest. The biological response to candlelight is subtle. It does not override stronger signals like caffeine, stress, or irregular schedules. Instead, it works quietly in the background, removing barriers rather than forcing outcomes. In a world filled with bright screens and constant illumination, candlelight offers a contrast. It reduces sensory input instead of adding to it. The eyes relax. The mind receives fewer cues to remain engaged. Over time, repeated exposure to dim, warm light in the evening can help reinforce a consistent rhythm. The body begins to associate that quality of light with slowing down. This association builds gradually, without effort. Candlelight does not demand attention. It allows attention to soften. This is why many people find candlelit spaces feel quieter, even when no sound has changed. The visual environment itself becomes calmer. The brain does not need to process sharp edges, intense brightness, or shifting colors. As the flame flickers gently, it provides a small point of focus without stimulation. The movement is slow. The light is steady. The space feels safe and contained. When used earlier in the evening, candlelight can help create a buffer between daytime brightness and nighttime darkness. It smooths the transition rather than making it abrupt. Once the candle is extinguished, the darkness deepens naturally. The eyes adjust. The environment settles further. The body continues its gradual shift towards sleep. Candlelight supports this process not by acting on the body directly, but by stepping out of the way. It removes unnecessary brightness. It avoids disruptive wavelengths. It keeps stimulation low. In this way, candlelight aligns gently with nighttime biology. It respects the body's natural rhythms, offering light without pressure, warmth without intensity, and presence without demand. A small flame, a dim glow, and a quiet invitation to slow down. When people talk about candle smoke, the conversation often turns to wax type. Paraffin, soy, beeswax, plant-based blends. Each is sometimes blamed or praised for air quality. But in most cases, smoke and soot are not caused by the wax alone. They are caused by imbalance. A candle burns cleanly when fuel, heat, and air remain in the right proportions. When that balance shifts, incomplete combustion can occur and soot may form. This can happen with nearly any wax if conditions allow it. One of the most common causes of soot is wick length. As a candle burns, the wick naturally shortens through self-trimming. If the wick becomes too long between burns, it can deliver more fuel than the flame can process efficiently. The flame grows taller, and some fuel does not burn completely. Tiny carbon particles escape the flame and appear as smoke or dark residue. Keeping the wick at an appropriate length helps maintain balance. A shorter wick delivers fuel more slowly, allowing the flame to remain compact and stable. This reduces the likelihood of excess carbon forming inside the flame. Air movement is another major factor. Candles are sensitive to drafts. Air flowing across the flame can pull fuel vapor away before it has time to burn completely. This disrupts combustion and increases the chance of soot formation. Even gentle air currents from fans, vents, or open windows can influence how a candle behaves. In still air, the flame maintains its shape more easily. Fresh oxygen is drawn in gradually from the surrounding space. Hot gases rise upward without interference. Combustion remains controlled. When air movement increases, the flame leans and stretches. The balance shifts. The flame works harder to stabilize itself, and incomplete combustion becomes more likely. The design of the candle also matters. A wick that is too large for the candle's diameter may overfeed the flame. A wick that is too small may struggle, causing irregular burning that can also lead to smoke. Proper wick selection helps ensure fuel arrives at the flame at a pace it can manage. Well-made candles are designed as systems. Wax formulation, wick size, and vessel shape are chosen to work together. When these elements are matched carefully, combustion remains similar across different wax types. This is why two candles made from different waxes can produce very similar air byproducts when burned under the same conditions. The flame does not respond to labels. It responds to physics. Soot particles are extremely small. When produced in large amounts, they may collect on nearby surfaces or inside containers. When produced in very small amounts, they may remain invisible, dispersing harmlessly into the air. In a balanced burn, most carbon particles formed inside the flame are consumed before they leave it. The glowing particles that create candlelight are part of this process. They exist briefly, release light, and then burn away completely. Problems arise only when this process is interrupted. Fragrance oils can also influence combustion if not well matched to the wax and wick. Some fragrance compounds evaporate easily, while others require more heat. If fragrance disrupts the flow of fuel or alters the flame temperature, it can contribute to incomplete burning. This is why fragrance load and formulation matter more than scent strength alone. A well-formulated scented candle burns cleanly because the fragrance is released in harmony with the wax and flame. Visual issues like mottling or oil separation in wax do not necessarily affect air quality. These are surface-level effects related to cooling and wax structure. They may change how a candle looks, but they do not automatically indicate poor combustion. Indoor air quality depends on how a candle is used as much as how it is made. Burning a candle in a well-ventilated but draft-free space helps maintain stable conditions. Avoiding strong air currents reduces flame disturbance. Allowing the candle to burn long enough for a stable melt pool to form also supports cleaner burning. Short, repeated burns that never allow the candle to stabilize can lead to uneven behavior. The flame does not have time to settle into balance. Allowing the candle to reach a steady state helps reduce irregular combustion. When a candle is extinguished, a brief puff of smoke often appears. This smoke comes from hot wax vapor cooling rapidly and condensing into tiny droplets. It is temporary and dissipates quickly. It does not reflect how the candle burned during use. The flame itself tells the story. A steady flame with a consistent shape and color indicates balance. A tall, flickering flame that produces visible smoke suggests disruption. Watching the flame can provide quiet feedback about how the system is functioning. In the end, soot is not a mystery. It is the result of a system working outside its ideal range. By keeping fuel delivery, air movement, and wick length in harmony, candles across many wax types can burn cleanly and quietly. The difference lies not in what the candle is made of, but in how well its parts work together. Balance keeps the air clear. Imbalance creates residue. And when conditions are right, the candle returns to what it does best, releasing light and warmth gently, without leaving a trace. Long before candles were objects of atmosphere or decoration, they were tools. They provided light where there was none, extending activity beyond daylight hours. The materials used to make these early candles were chosen not for refinement, but for availability. One of the earliest and most widespread candle fuels was tallow. Tallow is rendered animal fat, often derived from cattle or sheep. It was accessible and inexpensive, making it practical for everyday use. When solidified around a wick, tallow could be burned to produce light, but it came with clear drawbacks. Tallow candles tended to smoke. They often produced strong odors, and they softened easily in warm conditions. The unpleasant smell associated with tallow candles came from fatty acids and impurities that were released as the fat burned. These compounds did not always combust cleanly, leading to visible smoke and lingering scent. In enclosed spaces, this could make tallow candles uncomfortable to use for long periods. Despite these limitations, tallow remained common for centuries because alternatives were limited. Light was needed, and tallow could provide it. Beeswax offered a cleaner option. but it was not equally accessible. Producing beeswax required large numbers of bees and careful harvesting. As a result, beeswax candles were more expensive and less common in everyday households. Where beeswax was available, it was valued. It burned with a brighter, steadier flame and produced less smoke. Its mild, pleasant aroma contrasted sharply with the heavier scent of tallow. These qualities made beeswax especially desirable in places where air quality and cleanliness mattered. In medieval Europe, beeswax candles were often used in churches and other formal settings. The cleaner burn reduced smoke buildup in enclosed stone spaces. The steady light supported long gatherings and ceremonies. As time passed, new materials began to appear. Spermaceti, derived from the oil of sperm whales, was used in some candles during the 18th and early 19th centuries. It burned more cleanly than tallow and produced a bright, stable flame. However, its availability depended on whaling, making it limited and eventually controversial. Stearin, a purified fatty substance, emerged as another improvement. By removing impurities and concentrating specific components, stearin candles burned more cleanly and consistently than raw tallow. These developments marked a shift toward refining fuels rather than simply using them as they were. The most significant change came with the introduction of paraffin. In the 19th century, advances in petroleum refining made paraffin wax widely available. Paraffin could be produced in large quantities and purified to remove unwanted compounds. Compared to tallow, paraffin burned with less odor and more predictability. As paraffin became cheaper and more accessible, it gradually replaced tallow for everyday candle use. Households that once relied on animal fat could now use a cleaner, more stable fuel. The experience of candlelight changed quietly but meaningfully. Paraffin's consistency made it easier to shape candles that burned evenly. It supported longer burn times and reduced the buildup of residue on walls and ceilings. These advantages helped establish paraffin as the default candle wax for generations. Over time, additional refinements improved candle performance further. Blending techniques allowed wax properties to be adjusted. Additives helped stabilize burning and appearance. The candle became less about necessity and more about reliability. This evolution did not happen all at once. For many years, different materials existed side by side. Rural households might continue using tallow, while urban areas adopted paraffin. Churches retained beeswax for its symbolic and practical qualities. The transition unfolded gradually. What remained constant was the flame itself. Across all these materials, tallow, beeswax, stearin, paraffin, the flame followed the same rules. Fuel melted, vaporized, and burned. Light was released. Heat returned downward. The system repeated. The improvements came not from changing the flame, but from refining the fuel. As materials became cleaner and more predictable, candles became easier to use indoors. Smoke decreased, odors softened, light became steadier. The candle grew quieter in its presence. By the late 19th century, paraffin's affordability and performance contributed to the decline of tallow candles in everyday use. Lighting shifted from survival to comfort. Candles no longer needed to endure every condition. They could be designed for balance. Today's candles are the result of this long progression. They carry the same basic structure as their ancestors, but with refined materials that support cleaner burning and calmer behavior. From animal fat to purified wax, the journey of candle materials reflects a steady movement towards simplicity and control. As candles became common household objects, attention gradually shifted from simply producing light to producing it safely. One of the most important areas of change involved the wick itself. Early candle wicks were often made stiff, so they could stand upright in soft fuels. In some cases, this stiffness was achieved by adding metal to the wick's core. For a time, one of the metals used for this purpose was lead. Lead core wicks helped candles burn more evenly by keeping the wick straight as wax melted around it. The metal prevented the wick from bending or collapsing, especially in container candles. At the time, this was seen as a practical solution to a mechanical problem. Over time, however, concerns emerged. As scientific understanding of lead exposure increased, it became clear that lead was not a safe material for use in consumer products that produced heat or combustion. Even small amounts of lead released into indoor environments posed potential health risks. As a result, lead core wicks were gradually phased out. Many countries introduced regulations restricting or banning the use of lead in candle wicks. These changes did not happen overnight, but over years of increased awareness and updated safety standards. By the early 21st century, reputable manufacturers had largely eliminated lead from candle production. Modern candle wicks use safer alternatives. Some wicks include metal cores made from zinc or tin. These metals provide structural support without the health risks associated with lead. They help keep the wick upright, especially in container candles, while remaining stable under heat. Many candles no longer require metal cores at all. Advances in wick design made it possible to create cotton and paper wicks that support themselves through careful braiding and material selection. These wicks can curl, trim themselves, and maintain flame stability without added stiffness. Paper fibers are sometimes woven into cotton wicks to increase rigidity while preserving clean burning behavior. These blended wicks provide structure without introducing hazardous materials. Regulatory standards also influenced how wicks are tested. Manufacturers began evaluating flame height, soot production, and burn stability more carefully. A wick was no longer judged only by whether it stayed lit, but by how predictably it behaved over time. Safety testing considers how a wick performs as the candle burns lower, as heat builds in the container, and as wax composition changes during use. These factors help ensure that the flame remains within controlled limits from start to finish. The removal of lead did not weaken candle performance. Instead, it encouraged innovation. Wick engineering became more precise. Materials were chosen for how they interacted with wax and flame rather than for simple stiffness. The wick became part of a carefully designed system rather than a rigid support. This evolution also reduced the need for constant user intervention. Older candles often required frequent trimming to prevent excessive flame growth. Modern wick designs reduce this need through self-trimming behavior and balanced fuel delivery. As a result, candles became safer and more predictable for everyday use. It is now uncommon to find lead-containing wicks in mainstream candles. Regulations, combined with industry standards, have made safer materials the norm. Cotton, paper, and approved metal supports dominate modern candle production. These changes may not be visible to the user, but they shape the experience quietly. The flame remains steady. The wick behaves consistently. The candle performs its role without introducing unnecessary risk. The evolution of wick materials reflects a broader pattern in candle history. As understanding deepened, materials were refined. Hazards were removed. Performance improved through design rather than force. Today's candle wicks represent this refinement. They are lighter, cleaner, and better matched to the waxes they serve. They adapt as they burn. They maintain balance without demanding attention. In this way, modern safety evolution did not alter the candle's essence. It preserved it. The flame remains small. The light remains warm. And the system operates with greater care than ever before. Through regulation, material science, and quiet engineering, the candle has become a more reliable companion. Still ancient in form, but shaped by modern understanding to burn gently, steadily, and safely. As we come to the end of our time together, the candle remains what it has always been. A small system, a simple flame, a quiet balance of material, heat, and air. Across centuries, across materials, across cultures, the candle has changed very little at its core. Wax still waits in solid form. Heat still invites it to move. The wick still lifts fuel upward. Light still appears briefly and then fades. What has changed is how carefully this balance is shaped. Modern candles are not louder, brighter, or faster than their ancestors. They are calmer, more predictable, more refined. The same flame, guided more gently. Candlelight does not compete for attention. It does not demand alertness. It occupies space without filling it, offering warmth without intensity and presence without pressure. When the flame flickers, it does so within limits. When scent rises, it does so gradually. When sound appears, it fades as easily as it came. Nothing rushes. And when the candle is finally extinguished, nothing is lost. The wax returns to stillness. The room settles. The system rests, waiting quietly for the next moment of warmth. If you are listening as your body slows, allow that same balance to carry over. There is nothing else to do. No reaction required. Just a gentle fading of light, inside and out. Thank you for spending this time with Science for Sleep. May the glow linger softly in memory, even as the room grows darker and rest arrives on its own, at its own pace.